Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the
mana wirelessnya yang masuk
Cing, masuk.
masuk
Kayak didengerin, coba masuk kali sini. Ini lu naikin dulu Sarul. Cing. Itu dulu lagi di sini.
ingat lagi.
Ini buat apa ya?
Ini sebenarnya buat ini kamera. Nah, tuh kamera yang itu navigasi.
Oh, itu ya. Ini 2, yang ini buat tayang. Yang kemarin yang mana ya? Yang ini?
Iya.
Oh, nggak jadi.
Oh nggak jadi.
Kenapa emang? Oh, enggak, karena iya tadi karena nyari itunya.
Ya, itu udah nyari, saya nyari kok. Ya udah deh kalau gitu. Ini untuk presentasi, ini untuk audio sama hostnya.
Iya, ini
Ya
buat.
udah.
Ini diputar yang videonya Kitagawa, boleh.
Teknis.
Iya.
Iya.
Maaf nih Pak. Mana sih?
Udah dikasih belum?
Hah? Enggak. Ya udahlah, kita puterin aja lah. Iya, yang tadi aja ya Mas ya. Aja yang
research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future.
merah audiens mana ya Mas?
Audience. Ini.
Ini kan namanya 1001.
Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention, and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with two main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or RIDA. Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums. BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs, tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045 by consolidating science and technology resources, creating a resource ecosystem, and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
Kalau aku bilang sebenarnya aku jago banget, tapi aku pura-pura gak bisa gimana?
Ya nggak apa-apa.
In the world of science, there are discoveries that not only answer questions, but also open doors to the future of humanity. This is the story of Susumu Kitagawa, a Japanese scientist who was awarded the Nobel Prize in Chemistry in 2025. Susumu Kitagawa was born in Japan and showed a strong interest in science, especially chemistry, from a young age. The foundation Kyoto roots. Great discoveries are often rooted in deep foundations. For Susumu Kitagawa, that foundation was built in the cultural heart of Japan. His journey began at Kyoto University, where he dedicated his early years to mastering the fundamentals of chemistry. It was here that he earned his bachelor's, master's, and eventually his PhD in 1979. These years were not just about learning. They were about preparing his mind for a challenge that no one else saw coming. Kitagawa began his academic career as an assistant professor at Kindai University, then became a professor at Tokyo Metropolitan University. In 1998, he returned to Kyoto University and continued his fundamental research on gas adsorption. Far from the public spotlight, he began to question the rigid laws of materials science. While the world relied on hard, inflexible materials such as zeolites, Kitagawa began to explore the unexpected potential of coordination chemistry. At that time, the scientific community was skeptical. Could metal complexes really hold gas in a stable manner? In 1998, Professor Kitagawa silenced those doubts. He published a revolutionary discovery showing that porous coordination polymers, PCPs, could absorb gas at room temperature. This was the turning point. He didn't just discover a new material. He discovered that crystals could be flexible, pliable, and dynamic. Susumu Kitagawa is widely known for his revolutionary contributions to the development of metal organic frameworks, or MOFs. MOFs are porous materials composed of metal ions and organic molecules with a three-dimensional network structure and a very large surface area. These materials are capable of absorbing, storing, and separating molecules with remarkable efficiency. The discovery and development of MOFs opens up a wide range of new possibilities, from hydrogen gas storage, carbon dioxide capture, to the development of clean energy and environmentally friendly technologies. The summit, the Nobel Prize. Decades of relentless innovation brought him global acclaim from the Humboldt Research Award to the Solvay Prize. Yet, the highest peak was yet to be climbed. Finally, in 2025, the world stood in ovation. For his pioneering work in the field of metal organic frameworks, the Royal Swedish Academy of Sciences awarded him the Nobel Prize in Chemistry, along with Richard Robson and Omar M. Yagi, for their work on the development of metal organic frameworks. Susumu Kitagawa is now a distinguished professor at KUIAS and ICEMS. He serves as Kyoto University's Executive Vice President for Research Promotion from 2024. Kitagawa envisions a future in which shaft materials lead progress in various sectors of the environment, energy, resources, and health, calling the 21st century the era of gas. His contributions have earned him numerous awards. The introduction from a student in Kyoto to a giant of global science. He is the architect who taught us that the greatest potential lies in the empty space. This is the story of Susumu Kitagawa. Who knows, the next great scientist, it's you.
Porous coordination polymers, PCPs, also commonly known as metal organic frameworks, MOFs, are a class of porous crystalline materials composed of metal ions or clusters that are regularly connected by multi-identity organic ligands, forming a three-dimensional network with well-defined cavities, pores. The main uniqueness of these materials lies in their ability to combine the rigidity of inorganic crystal structures with the design flexibility of organic chemistry, allowing their pore properties, size, and surface functions to be precisely engineered. Structurally, each metal node acts as a coordination center that binds ligands, such as carboxylates, imidazolates, or phosphonates, to construct a repeating framework. This periodic arrangement results in an exceptionally high surface area, often surpassing that of conventional porous materials such as zeolites or activated carbon. The formed pores can range from micropores to mesopores, with their geometry and polarity tailored through the selection of metals and ligands. Functionally, porous coordination polymers excel in selective adsorption of gases, vapors, or organic molecules, energy storage, such as hydrogen or methane, heterogeneous catalysis, and drug delivery. The presence of open metal sites and functional groups on the pore walls enables specific interactions, such as coordination bonding, hydrogen bonding, pi-pi stacking, or van der Waals forces, that enhance the selectivity and efficiency of these processes. Another crucial advantage is their tunability. By altering the type of metal, the length of the ligand, or applying post-synthetic functionalization, the chemical and physical properties of PCPs can be optimized without modifying their fundamental framework. This flexibility makes porous coordination polymers a highly adaptable material platform for cross-disciplinary applications, ranging from energy, hydrogen or methane storage, environmental, pollutant capture, and healthcare, drug delivery and imaging, to industrial uses, separation and catalysis. Porous coordination polymers represent an elegant convergence of molecular design and materials engineering, offering controlled, functional, and customizable porous architectures, a vital foundation for next-generation materials innovation.
Indonesia, a land of immense wealth. We are one of the largest natural gas producers in the Asia-Pacific. Our gas reserves are abundant, stretching from the oceans to the depths of the earth. However, there is an irony. Despite being rich in gas, we spend trillions of rupiah every year just to import LPG. Subsidies are swelling, and the burden on the state is growing heavier. Why? Because distributing natural gas, whether LNG or CNG, is difficult. Building gas pipelines to every corner of the country requires massive infrastructure costs. Conventional gas cylinders are heavy and highly pressurized. But the future of Indonesia's energy is about to change. The answer lies in molecular-level technology. This is the beginning of a new history. A world-class research collaboration between the National Research and Innovation Agency, BRIN, and the Japanese technology giant, Kyoto University. Partnering with Professor Susumu Kitagawa, the 2025 Nobel laureate in chemistry and the pioneer of porous coordination polymer, PCP, technology. The BRIN research team, led by Dr. Jody Arya Laxmono, works directly with experts at ICEMS Kyoto University to bring this cutting-edge technology to our homeland. The secret lies in this magical material, PCP or metal organic framework, MOF. Imagine a porous nanopowder that acts like a super sponge. With just 1 gram of this powder, the surface area can be equivalent to a soccer field. It is capable of absorbing and densifying large amounts of methane gas, even at low pressure. This material is then inserted into the cubiton, a revolutionary cube-shaped gas storage container. Unlike heavy round steel cylinders, cubiton is lightweight, easy to stack, equipped with advanced IoT sensors, and much safer. This is the future of gas storage. Currently, proof of concept, POC, trials are intensively underway at the BRIN laboratory, ensuring this technology is ready for Indonesian conditions. The potential is tremendous. We can harvest methane gas from abundant palm oil waste, POME, in Sumatra and Kalimantan. Then store it in cubiton, and ship it to remote islands that are unreachable by gas pipelines. This is not just research. This is the path to red and white gas, replacing LPG imports with self-produced methane gas, saving trillions of rupiah in state funds. Together with Kyoto University, Atomies, and Yachiyo Engineering, BRIN is ready to deliver energy sovereignty for Indonesia.
Research is our strength to overcome any limitations. Innovation is the guiding vision that drives us towards the future. We cannot face this alone. We must stand together to make our vision a reality. Growing strong upon the land of Nusantara, a magical place filled with miracle and wonder. A land spanning 2 continents and 2 oceans, rich in culture and biodiversity. We and Indonesia are the necessary combination to realize the grand visions of the future. Like an orchestra, BRIN harmonizes research, development, assessment, application, and also synergies, invention and innovation in Indonesia. We created an ecosystem consisting of 7 deputies, 12 research organizations, and 85 research centers dispersed throughout Indonesia. Research Organization for Aeronautics and Space, Research Organization for Nuclear Energy, Research Organization for Energy and Manufacture, Research Organization for Earth Sciences and Maritime, Research Organization for Life Sciences and Environment, Research Organization for Electronics and Informatics, Research Organization for Social Sciences and Humanities, Research Organization for Archaeology, Language, and Literature, Research Organization for Health, Research Organization for Nanotechnology and Material, Research Organization for Agriculture and Food, Research Organization for Governance, Economy, and Community Welfare. BRIN catalyzing research and innovation to develop an advanced scientific ecosystem in Indonesia with 2 main targets. BRIN realizes the tremendous potential of the nation's youth in the field of science and technology. Thus, various research and innovation policies are being formulated to develop and cultivate human resources with high competence and aptitude in science and technology. Creating many excellent programs is a form of BRIN's commitment to researchers, innovators, and the general population from various disciplines across the nation. The research and innovation ecosystem quality improvement in Indonesia is also realized through the collaboration of various ministries, institutions, domestic industries, and regional governments, to name a few, by forming the Regional Research and Innovation Agency, or Rida.
dalam bentuk serunding.
Moreover, cooperation with various foreign research institutions continue to be developed through active participation as member of various organizations and international forums.
Tapi ngotornya malah kita nggak tahu. Pengalaman begitu terjadi. Pengotor yang ada di luar.
BRIN organizes research into a more effective and efficient process by integrating human resources, infrastructure, and budget from various research and development institutions. Oriented by a national research priority, BRIN routinely enacts comprehensive evaluations from various research and development institutions. This effort is supported through the continued management and improvement of various research and innovation facilities located across 17 regions of Indonesia, dedicated towards the development of science and technology. BRIN continues to improve our contribution to research and innovation towards national development by developing and revitalizing 4 areas of science and technology, or KST. An integrated area consisting of research laboratory facilities, testing laboratories, and industrial facilities for both startups and SMEs. Tenant office rooms, co-working space, meeting rooms, gallery rooms, and other supporting facilities. BRIN is here to manifest the future of a golden Indonesia 2045, consolidating science and technology resources and creating a resource ecosystem and research-based economical foundation. Transforming Indonesia as a global reference in the development and application of science and technology practices and the good of humankind. Nature is the source of inspiration. Knowledge is the foundation, and to be put in praxis for the sake of the nation.
Nggak dikerjain nggak bisa. Ya, kalau dikerjain nggak bisa. Dikerjain kalau itu ya mau nggak mau saya ngerjain.
In the world of science, there are discoveries that not only answer questions, but also open doors to the future of humanity. This is the story of Susumu Kitagawa, a Japanese scientist who was awarded the Nobel Prize in Chemistry in 2025. Susumu Kitagawa was born in Japan and showed a strong interest in science, especially chemistry, from a young age. The foundation Kyoto roots. Great discoveries are often rooted in deep foundations. For Susumu Kitagawa, that foundation was built in the cultural heart of Japan. His journey began at Kyoto University, where he dedicated his early years to mastering the fundamentals of chemistry. It was here that he earned his bachelor's, master's, and eventually his PhD in 1979. These years were not just about learning. They were about preparing his mind for a challenge that no one else saw coming. Kitagawa began his academic career as an assistant professor at Kindai University, then became a professor at Tokyo Metropolitan University. In 1998, he returned to Kyoto University and continued his fundamental research on gas adsorption. Far from the public spotlight, he began to question the rigid laws of material science. While the world relied on hard, inflexible materials such as zeolites, Kitagawa began to explore the unexpected potential of coordination chemistry. At that time, the scientific community was skeptical. Could metal complexes really hold gas in a stable manner? In 1998, Professor Kitagawa silenced those doubts. He published a revolutionary discovery showing that porous coordination polymers, PCPs, could absorb gas at room temperature. This was the turning point. He didn't just discover a new material. He discovered that crystals could be flexible, pliable, and dynamic. Susumu Kitagawa is widely known for his revolutionary contributions to the development of metal organic frameworks, or MOFs. MOFs are porous materials composed of metal ions and organic molecules with a three-dimensional network structure and a very large surface area. These materials are capable of absorbing, storing, and separating molecules with remarkable efficiency. The discovery and development of MOFs opens up a wide range of new possibilities, from hydrogen gas storage, carbon dioxide capture, to the development of clean energy and environmentally friendly technologies. The summit, the Nobel Prize. Decades of relentless innovation brought him global acclaim from the Humboldt Research Award to the Solvay Prize. Yet, the highest peak was yet to be climbed. Finally, in 2025, the world stood in ovation. For his pioneering work in the field of metal organic frameworks, the Royal Swedish Academy of Sciences awarded him the Nobel Prize in Chemistry, along with Richard Robson and Omar M. Yagi, for their work on the development of metal organic frameworks. Susumu Kitagawa is now a distinguished professor at KUIAS and ICEMS. He serves as Kyoto University's Executive Vice President for Research Promotion from 2024. Kitagawa envisions a future in which shaft materials lead progress in various sectors of the environment: energy, resources, and health, calling the 21st century the era of gas. His contributions have earned him numerous awards. The introduction from a student in Kyoto to a giant of global science. He is the architect who taught us that the greatest potential lies in the empty space. This is the story of Susumu Kitagawa. Who knows, the next great scientist, it's you.
Atau mengatur ponsel ke mode snap selama acara berlangsung. Atas perhatiannya kami ucapkan terima kasih.
Porous coordination polymers, PCPs, also commonly known as metal organic frameworks, MOFs, are a class of porous crystalline materials composed of metal ions or clusters that are regularly connected by multi-identity organic ligands, forming a three-dimensional network with well-defined cavities, pores. The main uniqueness of these materials lies in their ability to combine the rigidity of inorganic crystal structures with the design flexibility of organic chemistry, allowing their pore properties, size, and surface functions to be precisely engineered. Structurally, each metal node acts as a coordination center that binds ligands, such as carboxylates, imidazolates, or phosphonates, to construct a repeating framework. This periodic arrangement results in an exceptionally high surface area, often surpassing that of conventional porous materials such as zeolites or activated carbon. The formed pores can range from micropores to mesopores, with their geometry and polarity tailored through the selection of metals and ligands. Functionally, porous coordination polymers excel in selective adsorption of gases, vapors, or organic molecules, energy storage, such as hydrogen or methane, heterogeneous catalysis, and drug delivery. The presence of open metal sites and functional groups on the pore walls enables specific interactions, such as coordination bonding, hydrogen bonding, pi-pi stacking, or van der Waals forces, that enhance the selectivity and efficiency of these processes. Another crucial advantage is their tunability. By altering the type of metal, the length of the ligand, or applying post-synthetic functionalization, the chemical and physical properties of PCPs can be optimized without modifying their fundamental framework. This flexibility makes porous coordination polymers a highly adaptable material platform for cross-disciplinary applications, ranging from energy, hydrogen or methane storage, environmental, pollutant capture, and healthcare, drug delivery and imaging, to industrial uses, separation and catalysis. Porous coordination polymers represent an elegant convergence of molecular design and materials engineering, offering controlled, functional, and customizable porous architectures, a vital foundation for next-generation materials innovation.
Kontrol. Membuat struktur baru, strukturnya aplikasi yang orang mungkin penting banyak. Ini bisa dibuat dancing, ini tujuan dan waktu itu tadi itu ya baru juga berapa kali bisa seperti saya belum ada bulan
jadinya tim melihat ini kalau screen yang screen kita kayak gini ini zoomnya nggak akan bocor kan? Aku takut ya. Tadi aku udah admit yang mau masuk. Udah di setting kan? Biar mereka nggak bisa ya, biar mereka nggak bisa ngomong.
Enggak. Itu sih udah pokoknya yang sudah dipakai. Udah dikasih belum?
Nggak ada materi.
Ini sebuah ruang besar. Really happy to have you here. So, good afternoon, ladies and gentlemen. I'm Jangis Tiabudi from Research Center for Polymer Technology.
And I'm Evita Asria, also from Research Center for Polymer Technology.
So, on behalf of BRIN, National Research and Innovation Agency of the Republic of Indonesia, we warmly welcome you to this Young Scientist meeting with the Nobel Prize winner in Chemistry 2025, Professor Susumu Kitagawa. And this forum is aimed as the academic forum for us, especially the scientists, young scientists, and early career researcher. And also we have students from the high school and also university student. So
Okay, so this platform is to bridge the gap between pioneers and pioneering discovery and the next generation of future leadership. So our goal today is an open exchange where we discuss not just what science, but how the failure, the luck, the persistence required to push the boundary of human knowledge. This meeting is meant to be interactive, a space to ask questions, share ideas, and also lesson from both science and scientific journey itself.
So thank you very much. It's our great honor to introduce our special guest today. We have now with us Professor Susumu Kitagawa. He is a Nobel Prize winner in Chemistry 2025. We can give applause. Yeah, from his speech today, he was recognized for groundbreaking contributions to the development of metal organic frameworks, or known as porous coordination polymer, that has transformed research in range of many applications, including gas storage, gas variations in energy, environment, and also biomedical. Thank you very much, Professor Kitagawa, for your great efforts for the very first time to come to Indonesia and fly across nations to join with us today.
We are deeply honored also to welcome Mr. Daisuke Asari, Representative Director and CEO of Atomis Inc., a Kyoto-based startup focused on MOF or PCP and the next generation gas storage technology, Cubitan. And also, we are so honored to welcome Professor Bambang Subianto, Senior Scientist at the Research Center for Biomass and Bioproduct BRIN, and the Chair of the Expert Council of Indonesian Researcher Association, Perhimpunan Periset Indonesia, PP.
So,
we appreciate your presence with us today.
So let's give big applause for our listeners from today.
Okay, ladies and gentlemen, this session will have two parts. So the first part will be the question from us, the moderator, to our distinguished guests. And the second part, we open the floor to the question from the audience.
So now, Professor Kitagawa, thanks once again for being with us today, and we are really happy to have you here. As the very first time you come to Indonesia, what about the food here? What do you think about the foods here? The food is delicious.
Yeah, partly I'm familiar with this thing. Yeah, because the national close to the Japanese area, yakimeshi. Also, the Sunday is the yakitori. Yeah, I really enjoy that.
Nice. So we are pleased to hear from you.
Unfortunately, I have a problem with the chili.
Chili or spicy.
So the chili, very nice.
I see. Yes. Nice. We are really pleased to hear from you. So what about the vibes here? Do you think Indonesian is so hot or broad, or what do you?
Yeah, so hot and so cold.
So hot. Okay. It's extremely different. So, okay.
Yeah.
Thank you. So now we would like to bring this forum to inspiring discussion with our Nobel Prize winner in Chemistry 2025. So as we know from the manifest here, we have participants, which is our early career scientists and also young scientists, talented students from the high school, senior high school, and also from the university. So to inspire them. So could you tell us about the beginning of your work, and at the time in early 90s, what initially motivated you to explore metal organic frameworks?
First of all, I'd like to tell the young people about the motivation. So you have, of course, various types of motivation you have, but before that, the interest, okay, curiosity is very important. If you are interested in the sports and I don't know, the planting or something like that, so you can do is the best for this kind of things. And if you succeed in one this kind of issue, so you have to experience, okay, successive experience. This is very important. So this mind is very powerful to the another type of the curiosity or interest. So you can expand your world, the more. So that's very important, I think.
Okay, thank you very much for your advice.
Professor Kitagawa, actually, both of us moderator also working with more.
Yes.
So nowadays, the field in meta-organic frameworks become more popular and popular. But in the beginning of designing this material, it's not really universally accepted in the scientific community, right? So how is your biggest challenge when you work with this material, and how did you overcome this scientific doubt in the community?
It's very important. Today I give a talk about my interest, just the motivation and also the mindset is very important. So prepare the mind. So in the high school student, in junior high school student, in the experience of all the things, reading a book and the knowledge from the teacher, everything is okay, but they are something growing in your mind, in the one thing. So you just accumulate this kind of things, and ultimately one mindset you have. Okay? This kind of thing is very important. My case in the porous materials, one of my mindset in the space is very important. So that space is my focus in nanospace, where the molecule and the ion are playing. Okay? So just my mind said space is important, and one day I found this chemistry is important, and we synthesize things. But however, the public society, of course, and also even in the academic society, they have common sense. Common sense comes from the macroscale. Macroscale, you can see directly. You can, and visualize. So that means I synthesize porous material from the organic molecules. Organic means very weak, soft materials like that. So all the people think. For instance, in the case of building, stone building is very strong. Wooden building still strong, but paper building very fragile. So all the people say, oh, this is very, very, very fragile, unstable material. This is a common sense. So I prepared, I did experiments and got the data. I showed data. Most of the like this. Most of the people know. And after my talk, this is a wrong experiment and something like that. Several people, yeah. But I had a collaborator to observe the gas sorption. Okay. If I bought the instrument, okay, I was not the expertise, okay, in that field. So if I got the data, maybe I think, oh, I was wrong. But I had a good collaborator. So he did experiment and observe, measure this data. I believe in also his skill, expertise. So many questions, but I say, this is correct. This is my data. So that means you have the strong motivation and the curiosity. You are doing your own research or something. And also you have a problem. So you have a good, eyesight to judge, oh, this person is very fantastic. This person like this. So see good collaboration is very important for the future.
Yeah.
I think, right?
Thank you, Guru.
So it's important for us to determine and also have a big great motivations and confidence on what we curious about. And yes. Okay. So still connecting with my Akita's question. So at the beginning of your career as at the beginning of our career as researcher here, we have young scientists and also early career researcher. Sometimes it's kind of difficult for us to determine or shaping our research. For example, with mainstream research with well-equipped equipments and facility, or develop very frontier research for long-term application or long-term impact. So at that time in your own work, MOF was not famous. So how did you decide, commit and consistently working with metal organic compounds?
Yeah. So before I'm telling this, Kyoto University, in particular in the departments I belong to, this department has a sort of academic freedom. Okay. So academic freedom means, for instance, when I was a student, a graduate student, there's a professor, associate professor, looks big guy, yeah? But maybe you call professor, professor like this, but we don't tell this kind of thing. Just call the name. Okay? In Japanese, respectful word is san. San. Okay? So the professor Yamada-san, like this. Okay, flat. And also, professor, we are just behave as, for instance, I have this idea, I want to do this. And the professor said, okay, tell me. And okay, if you are so interested, do it. First chance, do it. But the other universities, if this guy made a mistake and no more new data or something, this professor said, okay, you made a mistake. You must follow my way, okay? Your experience like that. Okay, but my experience also, okay, and what's wrong? So tell me. And if so, do it again. That means do it again, second chance. And third, the freedom means there is obligation. Okay, so you have to produce a very nice data or something. So do it free, and finally, duty. This is a trend. This is my experience. So that's very important for your work based on the curiosity. Okay. So if you have this kind of atmosphere or scientific atmosphere, you can do it. But it's very hard to very free thinking, freedom in that case. So you have to see another place. No, but it depends on status, economic status, and also the other status and something like that. Okay, so anyway, even so, the discussion with the other people, in particular in the friends and the colleagues, just the discussion is very important. Okay, the communication skill is very important for the researchers. In particular, in the chemistry is a sort of the group research. So I will tell you examples. You know, music and symphony. There is conductor and players. But I like composer. Okay, composer. Okay, to create the music, symphony, harmony. Okay, so composer is very creative, but in the case, composer cannot do anything. We need 3 years, and the composer should conduct. Okay, so in the chemistry, you should composer and conductor. If you are composer, only composer, very difficult. Go to the mathematics. Okay, so chemistry is a composer and conductor. So today I went around the various universities after graduation. In the Kyoto is the national university. Then Kindai University is a private university. And the Tokyo Metropolitan University is a municipal university. Okay, city has this university. And then back to the national university. So I experience different society. That's very important. And ultimately, I can organize this kind of the scientists. Okay, so this kind of many various type of experience is very important.
Thank you very much for very insightful and also strong message for us to consistently work with what to like composer and conductor together. Wow, such a nice message for us. So we also want to hear perspective from our senior scientist, Professor Bambang, as the early scientist or student or early researcher here, how to shape or how to answer the such kind of dilemma, how for starting research with the mainstream research or with frontier research. So I want to hear your perspective about this one.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Yes, I think that's a very difficult question to answer. But yes, this is a chance for us to encourage young researcher to invite him. It's very important because as you know about the research thema is very linear, not like this one. So from the, as you know that Professor Kitagawa started this move research is 50 years ago. Yeah, 50 years ago with continuing program from him, continuing budget, and also continuing the measurement machine. I mean the for analysis. I think that my dream is someday the young researcher or young researcher from Indonesia have to get Nobel Prize. This is my dream. When I already in the kuburan. I think because this start from now maybe need for 2 years, 20 years or 30 years is no problem. But my dream is someday because as you know the BRIN already have a lot of measurement for the analysis for advanced technology, and also the not just the problem in Indonesia is the budgeting from the DIPA is very difficult. So I think the LPDP we can ask someday we can discuss with the LPDP to give the continuously the budgeting. So that's our strategy from now. So for the researcher association, yes, for the young researcher, we have every year we get so the theme of this year is reach to the Nobel Prize. So one of the why I invite him come here is just 2 years ago we visit the Kitagawa Sensei Laboratory, and this time she gives the presentation of what is the research from start to the end. And this time I asked him, since I first time research, to give the encourage young researcher, because my dream is the someday in the researcher got the Nobel Prize. So from now we have to ask the young researcher to linear research direction, and then the government have to support for the ceremony and also the budgeting. This is how to continue this for 50 years. That's our thank you.
Thank you very much. So consistent is the key feature or keywords that if you want to have a Nobel Prize in the future, and especially for our next generations, the senior high school student. I don't know. Yeah.
Okay. Maybe move a little bit to industrial challenge. So Professor Kitagawa, more nowadays already shifting from the laboratory scale to now is industrial scale. In your view, what's the view of what's the research area that mostly likely to have commercialization?
My research is very fundamental. So that we synthesize new materials only smaller than 1 gram. 1 gram. Tiny amount. That's enough. We can analyze the crystal structure and the properties, function. So that's it. So, but 20 years ago, many companies came to see me. Big companies, Honda, Toyota, and many companies. One said, you need 5 kilograms is materials. Impossible. So I said, because student is not the person in the factory. Student is just doing the research with their curiosity. Impossible. I just refuse this request. So that means no connection to the commercialization. Okay. Yeah. So nowadays the startups, even in Japan, we don't have this kind of culture to set up the startups. But right now, more and more we can establish startups. So the microwaver and sometimes I say that Higuchi, he is the researcher. He was very much interested in commercialization. So ultimately, he set up this company, Atomis, and invited Asari-san, okay, as the CEO, and the startups. So that means startups can do the scale up of materials, high quality production, and also the cost down. So that means new company, small scale, in this society. So nowadays, the future of the material is very big. Because, for instance, you are interested in this chemistry, you synthesize new materials, but just new material to the startups. Startups produce 5 kilogram, 10 kilogram, 500 kilogram, and so deliver this kind of material to the many companies. The companies are interested in this material. In one day, they produce the sort of the very commercialized, things. There's a big chance right now. 20 years ago, nothing. There's a big war in industries. So now we have this kind of bridge. And so the future. Today I said, I am interested in gas materials. So gas material, it was hard. Okay, it was hard. So porous materials can do it, touch and separate, and even just converting to the useful materials. Okay, so the future is the sensing also, and the delivering of drug in our body. For instance, there is chemistry using the sugar as the organic ligand, and the calcium as a metal ions, and force material, and deliver the drug to the tissue, and after its work done, this is decomposed into the sugar and the calcium. For instance, like that. So you should have a very crazy idea for the future, but you have 20, 30, 50 years. So the crazy idea is very good. So that means usefulness of the useless. Okay. Usefulness of the useless is
Apa yang ini ya yang dicabut? Ini udah penuh sih. Ini udah. Ini.
So I like crazy idea, but I don't like the crazy path. Okay. I like crazy idea. Crazy idea is very good.
Okay, thank you very much, Professor. Probably I would love to hear also from Mr. Asari as someone directly involved in scaling up MOF for industrial purpose. What are the biggest challenges when working with MOF in industrial scale? Is it cost, stability, or the market acceptance?
Everything. Yes, so it costs much money to establish the new material industries. So Kitagawa said, so there are big gap between industry and academia. So from the aspect of costs and the scalability, and of course the durability also. So we have to improve every aspects. So that it costs much money. So that we have to get collect much money to solve it. So that there are big hurdle. So material startup is a very tough task. So but my company's founder, Dr. Higuchi, so he is academic person, so he doesn't know the big hurdle between about establishing his material industry. Yeah.
So what about market acceptance now? Is it
market acceptance? Yeah, so the last point is cost. Yeah. Yeah, so they're right and other better carbon. Yeah.
it's also zero?
Yeah, zero right. So this history is quite long. So the currently the price is very cheap. So the competitors' cost is very So
This is very interesting. Probably for the next we will need to find a source that's not really expensive for synthesis in
but Indonesia has very big potential because Indonesia can produce nickel and copper. So such kind of material is very big potential for making the MOF, good MOF, stable MOF. So and there are young businesses, so many young scientists. They are comparing to Japan and other Western countries. So Indonesia has a very powerful MOF and other applications for MOF.
Okay, thank you.
Okay, so I have a question. How many kilograms of MOF you can produce?
Currently, so in my company, so I can manufacture 20 tons per year.
Wow.
And until 2027, I would like to expand the manufacturing to 200 tons per year.
Wow. That's easy.
20 tahun sekarang.
Yeah.
Yeah, of course, yeah.
Yang 95.
We would like to expand actually to in Indonesia.
Nice. Yeah. Great. Okay, so because my question has been answered from both Professor Susumu Kitagawa and also Radai Subhasari. So now we ready to open the question from the floor.
So please briefly introduce yourself, your name, and also institution. And keep your question concise so we can include question.
Yeah.
So
Any questions? You can also deliver in Indonesian because we have Professor Handoko that's very fluently speak in Japan. So yeah, okay, so you can. Yeah.
Thank you for it's very big honor for me to speak in our estimation. My name is Yuda. I'm from Badan Riset. I'm working with and it's something and I saw your background. You are coming from foreign. Your background is foreign name is right. So that is my background as well. And foreign chemistry, one of the first knowledge in foreign chemistry was Albert Werner, who published the octahedral structure for isosceles metal complexes, right? And then afterward, you mentioned in your picture that several years after that is polymer pollination. So what is the big difference between the mold and the polymer? And what is why this thing is relevant after 100 years later? Could be as training as now, right? Because the fundamental structure of transition metal complexes was founded nearly a century before. So why is this become trending after 100 years? This is my question.
100 years before.
Yeah, you talk about 1 years ago, yeah, our Nobel Prize to show octahedral metal complex structure. Okay, this is just one molecule, isolated molecule, but you are talking about the polymeric structure. But after that, okay, many people synthesizing polymeric structure. For instance, when just mix ligand and the metal, abruptly precipitate. A long time ago, this kind of material, they don't care about this because very difficult to investigate. What is the structure? Very sticky and okay, no crystal structure. It's very difficult to see, investigate. What is this? So they discovered this. So maybe in the long history of quantum chemistry, many people synthesizing the polymeric structure. Okay. This is background, I think. However, why I can do this? Today I show you. I selected kappa 1 metal ion because kappa 1 metal ion and organic binding is in the scientific token 100 kilojoules per mole, 100 kilojoules per mole. But the strong bond in the coordination case is more than 200 and 300 kilojoules per mole. Organic molecule, CC bond is approximately 500 kilojoules per mole. So, kappa 1 organic ligand binding is very big. So this is a key to get polymeric crystalline structure because in the reaction, this reaction made a lot of mistakes. It's fine for the other one, but so simply nothing happens. But bond is weak, so that means deformation curve. And so they stop because the solvent or this material stop. But bonding is weak. So we just dissociate and we do it to come here. So they gradually. So we can get the crystal structure. So kappa 1 provide very beautiful crystal structure. Don't. Okay. So we understand we can get very beautiful crystalline coordination polymer. Okay. So that was a few 50 years, 40 years ago. And space. We want to add space in this structure. So to do this, we have to get stronger bond. How we can make it? Because already we know the coordination structure. We can design this one. So we tried and error, and finally we can get the way of the synthesizing this time of the beautiful crystalline network structure. So the history is continuous, not the discontinuous case, just a continuous. But depending on the characterization method, crystallography, and so other things. Right now in the single radiation, even for the less than 1 micron crystal, we can detect the crystal structure. 30, 40 years ago, we have to grow big crystal. So Professor said to the student, did you get big one? No, Professor. Oh, do it again. But now, oh, you get shiny particle, something like that. Okay, we can get crystal structure. So depending on the characterization method. Okay. Now, you are standing with this kind of fantastic instruments. So next thing you have to do is your brain.
Okay, thank you very much. Another.
Dr. Hamza.
So thank you for the lecture. You mentioned this morning during your lecture.
Your name and
my name is Hamza. I'm not a chemist, but experimental physicist. So you mentioned this morning during your lecture, you were a theoretical chemist by training. I get PhD in Kyoto in theoretical chemistry, and then you switched to experimental chemistry. And could you tell us more about the reasons why you switched from theoretical to experimental chemistry?
Very simple. For that time in Japan, it's very bad time of the graduation. Got a PhD. No working place, academia. So I was very lucky, and I got this position, assistant professor position in University. But this is the story. And 6 months before, 6 months before, and I attended the code. Usually I attend the theoretical chemistry conference, but that time I attended the coordination chemistry society meeting, national meeting, and I was, very difficult to say, and I don't care about the respect this kind of field. Okay. Well, and say I attended. Okay. Many people. And before me, the one professor gave a talk. I found this is wrong because my background is quantum chemistry. But I understand the orbital and something like that. After that, I raise the hand. You are wrong. Okay, so these are a big professor. Who is this? Like this. And so just after him, I give a talk. In that audience, the professor to hire me. Yeah, sitting. And so 6 months later, he came to see me. Oh, you are something like that. And I was so lucky because otherwise impossible to get a position. But it's a hard decision. My experience in experiment is not so good. So, but this is a job. Okay, I do it. That's the case. But my career is very good because I know mostly a kind of the state of the art theory, something like quantum chemistry. So doing the experiment and the student brought the results. But they just brought result. But I say, you should think about why this happens. Okay, because I have the background. So this is a very good. So in the mock chemistry, my focus is the function. Okay. Omaria is the framework. So it's a genius of the kind of the framework, the architecture or something like that. My focus is the functionality. So we share that. This is the background.
Thank you. Very interesting.
Any other question? Wow. Maybe we want to from the student over behind. Students, yeah. Yeah. Young student, yeah. Please mention your name and what's your school.
Bisa lagi salah satu.
Morning. Hello, and let me introduce myself. My name is Anag Gudayakun Prashanaliseka. You can call me Agung. I'm from SMA Terpadu Krida Nusantara. And about my question, so I listened to your presentation last time, and I was wondering, how do you exactly make something so small, so molecular? And it was difficult for me to imagine it. And then in one of your presentation, you mentioned something about magnets. Now, making something with magnets made me realize that what if you place a magnet next to it? So I was wondering, would a MOF disassemble if you place a magnet right next to it? And would that mean that if you place a satellite like in your presentation, and would it explode if you place a magnet next to it? That's all for me. Thank you.
That's good. To make magnets and to get the force function just compete. When the magnets come from the spin interaction, you understand spin. Okay. Spin is just electrons. Yeah. So if the spins align parallel in that case, you can get a big strong magnets. But if we have space in between, the interaction is very, very. So this case bisa smooth banget ya transisi satu ke well. Switcher tuh mahal. So it's not that the magnet strong communication with the so the first I am interested in magnets and the conducting charge conducting also conducting position close to each other. Space means just break this communication. So space materials and this magnets and the conducting materials are complete. So this is stream of the space like that. But recently going come to each other. This is idea. We have a space.
Program BRIN udah ada kan dulu.
Why?
Sekarang menjadi proyek yang bentar. Saya pas isu.
So that means
Kenapa meninggal
the position is not that's right. So you think about this. So you have to think about next crazy idea.
So answering your question, okay. So anyone else want? Or Lady. Yes.
Iya Bu, kan vokal loh gitu.
My name is Lutfi Asari. I'm from Research Center for Metallurgy. My background is also chemistry, especially organic chemistry also. So it's
Ini yang itu N.
since my bachelor and also master degree. But my question right now is MOF is what the research is a proof that from basic research we could scale up until industrial, right? And it's not easy. I mean, this is what BRIN goal right now, that we would like to have the basic research that we could apply in industrial or in community. And my question is simple, that from Professor Kitagawa, how you prove that this materials, this MOF could expand or scale up and as industrial scale up, and for the Mr. that how you also believe that okay, this MOF is could be as industrial application, something like that, and have potential that is important for the future. Thank you.
I can tell you, my background is in the academia, so that means the tiny amount of novel materials is important. But you are taking that place. So,
Yang satu nge-zoom, yang satu
you have cooking recipe. So cooking recipe based on small size. 100 meters something like that. But industry means just that this is better. Okay. The mix and can you produce the same one? Okay. That's a big issue. So the industry also have this kind of fundamental question. So which do you like? Truly new materials, or just produce the large scale of material, the same property, same structure. So that's very important for you. Which do you like? And also he knows, Asari-san knows, and you scale up, and also cost down. How do you okay. If you are interested in this is also a very fantastic job. So just ask yourself. I like fundamental. I don't care society. I don't care the society. Just my curiosity. But after Nobel Prize, I have to say something. But nothing there. Create new things.
Yeah, scale up is a very big problem for material. So I was working for certain pharmaceutical company. So then I was seeking the new materials for immunostimulant. So then also the scale up is a very big scale up was very big program. So, but it's possible. I know. And the semiconductor material also. So the many companies are developing the new manufacturing process, and they realize the very accurate semiconductor. So the scaling up is possible, but it costs much money. So it has big hurdle. Yeah. So maybe the most researchers use solver-thermal method for synthesizing MOF. It requires big amount of organic solvents and high temperature and high pressure. So maybe many people so the manufacturing process is very difficult. So maybe the cost down is very big hurdle for realization. But actually, we use the mechanical synthesis process. It doesn't need big amount of solvents, and synthesis condition is ambient condition, so it doesn't need high pressure and high temperature. So that it is very eco-friendly and very cost-effective manufacturing process. And other more ventures utilize the hydrothermal method for synthesizing MOF. In that case, so it is not organic solvent, so just the water, so that it is not dangerous, and it doesn't release the carbon dioxide in the synthesis of MOF. So yeah, so comparing to solver-thermal method, hydrothermal process is very eco-friendly and cost-effective. So maybe the near future, another manufacturing process would be discovered, I guess. So more price will dramatically decrease, and many applications will be realized, I guess.
Okay. So because the time is limited, so we are ready to close. Thank you very much for your question. So we hope it's inspiring. But before we close, we want to hear the top advice from Professor Kitagawa, especially on the young scientists and then the students and also university and doctoral student here. What should we do in the future, especially to shaping our research to be Nobel Prize level research?
Yeah. I want to say the government. Yeah.
So government people.
Invest, okay. Next 2 years, okay, to get a Nobel Prize. So right now it's difficult to find who is just a candidate of Nobel Prize. But invest next 20 years or 30 years, invest fundamental science more and more. Okay. Let's set up the institute or university having the academic freedom. So that for the future from here, for the future the Nobel laureates. So they have a crazy idea. But in the next 20 years, investing, okay, funding investment. So that means the crazy idea is changing, and reality and more theories and materials like that. So please look for the next 20 years. So that's very important, I think.
The end of our
meeting. Professor Kitagawa, thank you very much for your kindness and sharing how theories will drive discovery, and your wisdom is been truly inspiring for all of us. And also, thank you very much for Professor Bambang and Mr. Daisuke Asari.
Yes, and to our participants today, we hope today's discussion encourage you to think boldly and follow your curiosity as you shape the future of science. So please once again join with me to give applause with our representative.
This meeting, but before that, we will take a photo session. Yes. So probably, maybe all the participants can come to the stage, huh?
Yeah, can come in front of the stage.
Okay.
Okay.
So probably,
We'll stand up.
Yeah.
Yeah.
yes, okay.
And the participants can stand up.
Yeah, okay.
Siapa? Ibu mau? Enggak. Imut ibu ya.
Boleh di bawahnya. Boleh di
Ceria. Baru kenal aja.
Ya, selfie sama stranger.
Oke, kita mulai. Saya kasih aba-aba ya. 1, 2, 3. Oke, gaya lain. 1, 2, 3.
Oke, kayak bebas.
Kayak bebas, oke. Terima kasih.
Karena kimianya beda bidang. Terus kalau ibu berarti Oppenheimer baru, ayo satu gitu.
Ya, yang aku lagi aja lebih ke arah itu variasi,
Chernobyl.
iya.
Nah, gitu.
Banget. Itu ada rumit apa namanya batuan uranium dari sekian.
So after this, we will join to more activities. Gas mayor.
Nanti ada bentuk besar dari batuan itu dari jadi berapa? Maka reaktornya jenis apa? Itu beda-beda.
Kayak gitu bener-bener lupa. Kalau ngulang-ngulang dikit bisa lah.
Hasil foto. Sekarang foto sama aku. Foto sama aku.
Jemput gue.
Kali ini.
Sini nih.
Kamu mau fotoin nggak kita foto bertiga?
Oh, iya.
Apa kamu jadi setannya?
Ah, males dia.
Cek. Bapak Ibu, adik-adik, ada yang merasa kehilangan tumbler? Tumbler Pertamina, bukan tumbler tuku ya. Tumblernya mereknya Pertamina. Nanti diambil di meja panitia ya. Mohon disampaikan. Terima kasih.
Mau di sini? Oh, sorry.
Backgroundnya itu.
Ah, udahan, Bu. Aduh, harusnya aku kasih tarif ya. Pasang backdrop berapa? Foto di depan backdrop.
Oh, mau dipotong.
Iya, aku tadi kan buat foto bersama itu kan pada ngambil foto di situ. Udah belum? Udah.
Ya, udah kayaknya.
Oh, sudah.
Iya, Pak, saya pengen pulang nih, nggak enak badan.
Ya,
Iya, dari kemarin malam dia. Rumah.
berapa hari? Gini.
Jadi emang malam. Semalam doang. Malam jarang jauh dari istri. Ya. Pelan-pelan, pelan-pelan.
Mainnya jauh.
Wah,
Sampit.
Udah nggak main sekarang dari tahun lalu.
ya, banyak berlian sudah ya.
Jauh dari